up and finishing up here with this tunneling discussion. So I also just wanted to draw your attention to the learning goals here. So the last ones here to talk about, be familiar with the concept of tunneling. So I talked about that in, I think it's lecture 10A. So know how to solve the Schrodinger equation for the three regions of the tunneling problem. Mike, right, I went through that. So be familiar with how to solve the tunneling problem with 4 equations and 6 unknowns. So that's, again, be familiar. Don't have to write a PhD thesis on it. And also recall, and I'm going to review this here in just a moment, but we were able to reduce the 4 equations, we were able to reduce the 4 equations and 6 unknowns to 5 equations and 5 unknowns. Okay, so that's kind of what I want you to be familiar with. And the last thing that I'm going to discuss today is be familiar with the tunneling characteristics of particles with differing masses and energies. All right. So let's get into it. And so I also want to clear up this slide right here. I was watching this, reviewing this at the end, and of course I did another slightly dyslexic thing where I wrote these things backwards. So recall here where we left this, we came up with 4 equations and 6 unknowns, right? All of these normalization constants that we have to find simultaneously for the various regions, the 3 regions of the tunneling problem, okay? And so last time, so I got this transmission thing backwards. And so the idea is the 5th equation that we can come up with, right? So here's 1, 2, 3, 4, and then 5, right? Is noting that the transmission probability of this particle is going to be a ratio of its amplitude in region 3 to its amplitude in region 1. So I have those backwards. So we'll say it's, wave function of right moving particles in region 3 over the wave function of right moving particles in region 1. And of course, we recognize here that the reflected wave in both region 1 and 2, those are important for knowing how the particle is going to, undergo that forward motion all the way through, okay? And so what ends up happening is this idea now reduces to be the square modulus of a prime, right, the region 3 normalization constant, over the square modulus of the region 1 constant, okay? And so what we can do from here, so the reason why this gives us a 5th equation is because if we do some algebra on this situation, oops, let me open up my cheater notes here, okay? If we do some algebra, so I'm going to say ... algebra, we can actually come up with an equation for this transmission probability. And that looks like the following. So I'm not going to require you to do this algebra, but this comes from, I'll rewrite that again, a prime squared. Let's make that look a little bit clearer. So the a prime squared over a squared, okay? And all of that, when we do the algebra, plug in those equations, okay, really, by using the wave functions, right? Then we get this equation, okay? So here we notice that we no longer need K, we only need kappa, okay? So I'll remind you that kappa was equal to 2m v minus e over h bar squared, all square root. And now this eta that we see right here, okay, that's the ratio of E over V, okay? So that is a ratio of the particle's kinetic energy to its potential energy, all right? And so now what we see here, there's a couple things that are going on in this figure, okay? So this left figure here, you can see incident energy in terms of E divided by V. Okay, so this figure is when E is less than V, right? Because you can see, You know, for example, at this number 1 right here, that's when E is equal to V, right? And then similarly right here on this graph. But now you notice, you know, for the rest of the scale on this right graph, this is where E is greater than V, okay? And so, of course, the transmission probability is going to be a number 0 to 1. 0 meaning 0% chance that it transmits through. So when T is equal to 0, no tunneling is possible. So in other words, it doesn't make it out of the other side, okay? And of course, when T is equal to 1, this is like the perfect case where the particle just moves through there unscathed, right? Which, as you can see from the graphs, is also not possible. It can't quite hit up to that 1 value. And I'll show you, I'll describe these two figures in a moment, okay? And so what do we have going on? So now there's also these numbers, okay? And those numbers have the value of L, let's see here, times root 2mv over h bar squared, okay? And so what these numbers are indicating, they're showing us what happens as the length of the box is increased, okay? So for example, you can see on the scale here, 2, 4, and 10, right? So as you can see, as the length of that box decreases, you know, if I pick a point like, let's say, right here for the same constant incident energy, right? Let's suppose the incident energy is 80% of the potential, okay? So if, let's say, the potential energy was 10 electron volts, the incident or kinetic energy would be 8 electron volts, right? So now you can see if that's the case, and if this length of the box is fairly narrow, there's a really high probability that it'll make it through, like 35% chance, okay? So now, and that 35% chance is what really gives us the scaling down of the amplitude, okay? And so really that is to say 35 out of 100 particles will make it through, all right? And so now if I scale down here, so you can see when the length of the box is doubled to that value of 4, the transmission probability goes way down. And if the length of that box goes all the way up by, you know, to a factor of 10, so 5 times greater than it was for that number 2, you can see it doesn't transmit at all, right? And so for that case, when the length, you know, is that factor of 10, so that's a relative scale, right? But you can see we have to really crank up the energy for it to transmit, okay? So now something also cool happens when we look at the situation when E is greater than V, okay? So you can see this curve right here to the same number 10 curve, so it's really starting to take off, and now it really jumps up. And what's pretty cool about this, what I think is cool about this, okay, in the case when they're 1 to 1, right, it just shoots way up to damn near 100% intensity, or 100% transmission probability, very close to it. It's not, it doesn't quite hit that value. But then what's also neat is as you increase that incident energy, you get this oscillatory probability, which is just a function of this being a wave property, okay? So when the length of the box is quite narrow, this number 2 right here, so that's where this curve takes off. And interestingly, it doesn't take on that oscillatory nature. It's taking on some exponential growth, okay? And so that just gets into some of these peculiarities of changing the length of the box or changing the energy of the particles as they're fired at the, or not really the box, but the barrier, okay? So now, what happens when we change the mass of these particles, okay? Well, for a same incident energy, so if let's say my heavy particle and light particle had the same kinetic energy, right? then the heavy particle will experience more dampening than the light particle. So in other words, it'll have a smaller transmission probability for the same given kinetic energy, which is kind of to be expected. And so now to demonstrate that, this is what you're going to do in your Mathematica assignment. And I'm just going to demonstrate this through the two graphs that I have. And we'll get into this more in our Friday discussion. But here what I have, these are realistic calculations using electron mass. So this first graph. So I actually used the electron mass, and I made the barrier 10 electron volts. And what I have here on this X scale is the length of the barrier, okay? And you can also see now these are looking at different incident energy levels. So for example, 10 electron volts is the potential energy barrier for this tunneling problem that we did here, that I did here. And then so when E over V is 0.5, that means the kinetic energy of the electron is 5 electron volts, right? So when it's 0.7, it's 7 electron volts. When that number is 0.9, it's 9 electron volts. And as you can see, right, the higher that incident energy is, the longer of a distance the electron can tunnel, right? So like if I look at the, let's say 3 angstrom, and again, these are realistic calculations, real numbers that I put in here, okay? 10 electron volts barrier, and let's say 3 angstrom, you can see only the particle with 9 electron volts has any decent chance of tunneling through, right? And so as you can see, as the kinetic energy gets smaller, that tunneling distance, you know, where it can actually make it through really falls off. But all the same, we notice that this is a pretty big scale that electrons are able to tunnel over, you know, between, you know, 1 and nearly 4 or 5 angstrom. That's a really big distance. But check out what happens when I change this to a proton. So now this is proton tunneling probability, okay? Same barrier energies, 10 electron volt potential energy, but now look, even the most energetic proton here, the one with 9 electron volt kinetic energy, can't even make it a quarter of an angstrom, right? It makes it, you know, maybe 1/10, maybe 0.15 of an angstrom, but that's it. So oftentimes in experimentation, when you want to prove that tunneling is a valid mechanism, what people will often do is compare the experimental result with a proton versus that with deuterium. Because even the proton falls off at a really, really short distance, okay? If I were to replace this proton with deuterium, right, then there's no way the tunneling will happen at all. And so that's a really good indication that people use experimentally to prove tunneling is a valid mechanism, specifically in kinetics. When they see something is happening so fast, the only way it could happen is if, you know, a proton tunnels right through a barrier in the case of a proton transfer reaction. You replace that with a deuterated sample, and if the reaction cuts off, then very likely tunneling was involved in the reaction, okay? So heavy particles, you know, typically a proton, and light particles, typically an electron, or you could even compare protons and deuteriums, or even protons, deuteriums, and alpha particles, right? You can compare all these different masses, okay? So now what we have over here is now going back to the particle in the box problem. Hopefully this looks familiar to you, okay? And what I want you to recall, when we originally did the particle in the box problem, when we said this is an infinite square well, our wave functions looked a little bit differently. They actually looked like this, okay, with no tunneling whatsoever into those barriers, because we put the particle in what we call an infinite square well. Well, as it turns out, because of this tunneling, and because we're never going to have infinitely large potential energy boxes, right? Then realistically, in this particle in a box problem, or particle in a sphere, particle in a cube, we do see a little bit of tunneling on the borders of these boxes. So some small amount of tunneling is possible into the box barrier, okay? And then similarly, if we go up to the n is equal to 2 level, we still see features that we saw similarly to the particle in a box. However, right, more tunneling into that barrier. And what I also want to indicate, okay, so I'm just going to write this equation down directly. If from this we can also predict how many what I will call bound states are in this potential energy box. And by bound states, we mean states that are in that box that very likely can't get out. We will later call these bound states orbitals, okay? So there's an equation that comes as n minus 1 is less than 8 mvl over h bar squared square root is less than n, where n is the number of states. And what's important to note about this relation here, what this predicts is, you can see now the number of bound states, that's n, okay? It will increase as the length of the box gets wider, and it will also increase as the depth of the well gets bigger. So in other words, as the potential energy increases, and now we're kind of moving past this tunneling thing and combining this idea of tunneling and the particle in the box, okay? If the potential energy increases, which we can think of as the well is getting deeper, okay, we get more states. If the length of the box gets wider, we also predict to get more states. And that's actually a direct result from statistical mechanics. So here I have a really cool simulation to show you. I've put a link of this on the course website, okay? And what's really neat about this is, I'm pretty sure that this is LabVIEW. And this basically is doing this, particle in a box with some slight tunneling simulation for us. And so I'm going to go ahead and run play. So this is going to show us the time dependent. And so now I'm only looking at the probability density. But when I put on the wave function, and I've also told it to show me the real part and the imaginary part, I can see how the wave function is evolving in time. Okay, this white part, magnitude, that's more or less showing me the psi squared, the probability density. And what's also cool is each one of these correspond to different energy levels. So there I can pick psi 2. So this would be the first excited state rather. So I can go and pick psi 3, and you notice they look kind of like what we expect. But what I want to show you, so in this model here, let's just look at the probability density, okay? What I want to show you is I've got a really cool way of demonstrating how there is just a little bit of tunneling at the edge of these borders, okay? And it's really difficult to see, but right, I can change the width of this well on this simulation. And notice here when it's a really narrow width, only 0.2 nanometers, there's only predicted to be 2 bound states that can fit in there. And look at this crazy, insane amount of tunneling that can happen there, right? So if you look at the purple line, if I widen that out, and of course, as you can see, as I'm widening it out, I'm getting more bound states, right? So I'm going to widen it out to this dotted line right here. Okay, great. So see this dotted line. And now if I follow the dotted line all the way down, and let's go back to the ground state, you can see not much tunneling characteristic outside of that border. But what if I go nearly to the top of the well? What if I excite something all the way up there? Look at that. There is definitely a good amount of probability of finding that electron outside of the well. And in part, that's because we've nearly ionized it out of this potential energy well, okay? which is really cool to think about, how tunneling can play a role in the ionization of something, like literally kicking the electron out of this well. Okay. So also what's cool is I can change the depth of this well. So, I do that by grabbing this one. So now that's a 10 electron volt, barrier. So as I make it bigger and bigger, look what happens to my little tailing, the little tunnel tail there at the bottom, right? So as I make that higher and higher and higher, it has a harder time tunneling out of the barrier, which is what we would kind of expect based on our discussion. So now what I want to show you, what's really cool, what's more realistic, electrons don't exist in these little square wells. It's actually a well, like this is actually the Coulomb potential, right? And so what's really neat there, you can see in the ground state, it's predicted to be, the right probability density somewhere right there in the middle. But now if you look at this, I've got some bound states up here that get very, very close to being, it looks like they should be tunneling out. They should have some probability out there. But there is such a strong pull from the Coulomb potential in here that it's keeping that electron bound. So in other words, we still have a lot of things to consider in building up our wave functions to describe atoms. We haven't even included the fact that there is a positively charged proton keeping that negatively charged electron sucked in to this potential energy well. So we're going to have to build that in our coming equations. So in the last couple things I want to show you about this figure. So this is really cool. So there's the two-well diagram. So this is a simulation of molecular bonding. So you could think of each one of these wells as a different nuclei, okay? And where you can see really, so now at this ground state, right, they look pretty well separated. But if we start to go up in these higher levels, you can actually see that there's shared probability between the two nuclei. And we're going to explore that in more detail. And what's also really cool in this simulation, here's the mini well simulation, and we'll just do the 1D Coulomb. And this is actually a simulation of metals, right? Of a bunch of metal atoms existing in this mini well, or what we call this banded structure, okay? And so this is also really cool to see how you can change this. We can, oops, I thought I could do more changing the space of the atoms. But as you can see now, the wave functions get really complicated for these figures. So I'd encourage you to play around with this. This thing is really, really cool. Okay, folks, that's it for the lectures on translations. Next, we're going to be moving into talking about vibrations. All right, I'll see you later.